The fact that enthalpy and many other and all the other thermodynamic variables for that matter, but specifically enthalpy, is a state function. The fact that it only depends on the initial and the final state, not the path that it took the reaction to go from the initial state, the reagents, to the final state, the products, give you a really nice property, which is, well, it's called Hess Law because it was the first chemist to propose it. That you don't have to measure all the changes in enthalpy of all the possible reactions that you can think of. That if you have a reaction that you're interested on and you don't know the changing enthalpy, but you have other reactions that involve those chemicals, reagents, and products, and you do know those changes in enthalpy, you can manipulate those chemical equations to give you your target equation, and that will allow you to calculate the change in enthalpy without having to go to the lab and measure it. Hess Law says that if you have a reaction that can be carried out in several steps, the overall change in enthalpy will be the sum of the enthalpy changes for the individual steps that got you there. So, for example, I want to calculate or want to measure the changing enthalpy of the reaction of burning methane with oxygen. So methane, CH4, 2 moles of oxygen gas produces CO2 gas, 1 mole, and 2 moles of water. And I'm going to have it as liquid water. So this is what I call my target equation. And I don't have that changing enthalpy, but I happen to have a couple of different changes in enthalpy. I know, for example, what is the changing enthalpy of burning methane with oxygen and making water in gas form. And it apparently is minus 802 kilojoules. And then I also know that to go from 2 moles of water in gas form to 2 moles of water in liquid form, that releases the changing enthalpy is minus 88 kilojoules. So if I add up 2 steps, those 2 equations, I can come up with my target equation, which is what happens when you burn methane with oxygen and you make CO2 gas and water liquid. And because I have added the 2 reactions, I add the 2 enthalpies, and that gives me minus 890 kilojoules. This is a really nice property because there are many reasons why you might not want, or maybe you can't, measure a particular change in enthalpy. The reagents or the products might be, or that particular reagent, most likely the particular product might be dangerous to make in that form. Or the changing enthalpy sometimes can be very small. So you measure these changes in enthalpy with something called calorimeters, and they have heat leaks, and they have imperfections, and they give imprecise measurements. So if the change in enthalpy is very small, it might be difficult to measure, and you can make a lot of experimental error. So there are quite a few reasons why you might not want to, or you can't measure all the possible changes in enthalpy. So you can use this property, the fact that because only the initial and final step. The initial and final steps are important, the reagents and the products, but the intermediate steps do not matter. It doesn't matter how you get from A to B, it just matters that your initial state is A and your final state is B. That can be used to calculate many changes in enthalpy, that just by using tabulated data, that otherwise you would have to literally measure one by one. So I'm going to ask you to put that information in an energy diagram. So the first thing I'm going to ask you is, could you draw an energy diagram that will represent this reaction, the methane and the 2 moles of oxygen to give you CO2 and 2 moles of hydrogen and liquid? Stop the video now, please. Okay, so I hope you stop the video and have a go at the exercise. How would I go about this? So an energy diagram. So if I draw in the y-axis change in enthalpy, and in the x-axis something like state of the reaction, or reaction, how the reaction progresses. So I look at my reagents and my products, and I look at my change at the changing enthalpies, minus 890. The minus tells me this is an exothermic reaction. This reaction is going to release heat, that amount, 890 kilojoules. That means that the reagents have enough energy to make the products, and a spare one that they release to the surroundings. That means that the reagents are going to be higher than the products, and that gap between the reagents and the products is my 890 kilojoules. So then I draw the reagents here, and I put the quantities and the state, and I put here the products, CO2 in gas form and 2 moles of water liquid, and this difference that in enthalpy is minus 890 kilojoules. Okay, so that is if the reaction would happen in one step. How would this diagram look like if it happened in 2 steps? So now I'm going to ask you to stop the video again and add these 2 extra pieces of information to our diagram. What would happen if the reaction, instead of happening in 1 step to produce liquid water, you went through an intermediate step of producing, the reaction happening but producing water in gas form, and then the water in gas form was condensed to liquid water? How would you modify your energy diagram to reflect those extra 2 steps? Stop the video now, please. So I've got my energy diagram, and now I want to add the 2 extra reactions. The first reaction is the methane and the 2 moles of oxygen, both in gas form, to produce CO2 in gas form and 2 moles of water in gas form. And that is minus 802 kilojoules. So this is a qualitative note, like a sort of, there are no numbers in those scales, but I would say that, let's say that 800 joules is something somewhere around here, most of that length of that initial arrow. So I've got my reagents already here written, and now my products, again, this minus is this energy releases energy, so the products are going to be in a lower state, energy state, CO2 gas and 2 moles of water in gas form. And the next step would be to convert the water in gas form to the water in liquid form, and this is what I would put here. Let's put it here. So I would have the first enthalpy, which would be minus 802 kilojoules, and the second enthalpy, intermediate enthalpy, would be minus 88 kilojoules. And here it gives me all the information. I've got the numbers of the enthalpy changes, I've got the state of reagents, etc., all in a graphical form that allows me to spot quickly which chemicals have higher energy than others.